So thank you everyone for joining this session. I'm Uri Yerushalmi. As said, I'm the Chief AI Officer and co-founder at Fetcherr. A few words about myself before we begin. So I've been building decision-making systems, quantitative decision-making systems for more than 3 decades now. And some of these decision-making systems were based on algorithmic trading, high-frequency trading, as I was head of AI division in an algorithmic trading company. And my academic background is a PhD in computational neuroscience, and some of the slides, hopefully when the slides show up, that you'll see are based on biology and computational neuroscience. Generally, we at Fetcherr deploy decision-making systems in various enterprises. And today I will discuss some of the concepts behind these decision-making systems. The decision-making systems are naturally quantitative, and there are many lessons that can be learned from biology, from evolution, that are inspiring and have inspired the architecture behind our decision-making systems. Initially, for more than a decade, I was in a trading firm making algorithmic trading. And many of the concepts behind trading, today almost 20%, 90% of the volume in NASDAQ and other capital markets is based on algorithmics. And back then, in the trading firm I was in, these decisions were based on models that are predicting the future market dynamics in NASDAQ and in New York Stock Exchange and other markets. And then you all probably know that most of the capital markets got into a situation where they are very based on speed. And I was always interested in making the right decision, not based on speed, but based on being smart. And that's why we turned into other markets that are not capital markets to make the decisions. I will talk about the next slide. So there are certain principles, as I said, that have designed our decision-making systems, and some of them are based on biology. And speaking of biology, we have these biological decision-making systems, our human brains, and they have evolved over hundreds of millions of years and have produced certain regions that are specialized in processing different kinds of data from the natural world and solving different kinds of problems. For processing, for example, visual data, we have our visual cortex. For planning, we have the prefrontal cortex, and we have different regions for processing sound and taste and touch and so on. But what's important is not the exact location, the precise location of each of these regions. What's important is that it shows that the architecture of such a decision-making system needs to reflect the complexity and the structure of the environment in which the decisions are made. Now, let's compare that with what happens in agentic workflows that are making decisions in the business arena. These workflows are always in their center, they have a language model. There are some layers that take care of harnessing, or maybe some visual models too, but at their core, these systems are based on language models. These language models are extremely powerful, but still, they are trained primarily to generate text and process text. And that raises the question of, are these language models, that these language-centric architectures, are they sufficient for making business decisions? Because there is a correlation between what happens in the natural world and the structure of the brain that makes decisions in the natural world. There are some first-class citizens in the natural world of images, of sound, of movement, that are projected into the structure of the decision-making system, the brain, in that natural world. But we don't see that correlation in the business world. The brain, the central system in the agentic workflows is based on language, but the main concepts in the business world are concepts like price, like supply, like demand, and these concepts are not the first-class citizens in this decision-making system. That's why we in Fetcherr, we believe that language models are not enough for making quantitative decisions. For making such decisions, the decision-making systems need to be able to really sense the market, to have the market sensation, to be able to forecast the future market dynamics, to be able to simulate various scenarios, and among these scenarios to choose and optimize the best decisions and act on them. It needs to quantitatively be able to evaluate the rewards of every such decision. Of course, language models and harnessing layers are essential here, but the optimal decisions are dependent on tools that need to be trained directly on the dynamics of the business environment. That's why we in Fetcherr, while most of the AI community was focused on language models, we were building during the recent years our market models. These market models are not trained solely on text. They are trained on the market dynamics, and they are the core of the systems that in various enterprises today enable autonomous quantitative decisions. The market models can be compared to other deep learning models because all of these types of models are based on same techniques, same types of layers of deep learning and neural networks. But there's a tweak here where while the language models are trained on text and visual models are trained on images or video, our market models are quite similar to large world models, while large world models are trained on data or simulative data of the physical environment. The market models are based on data of the market environment. So looking deeper into that, the basic concept of language models are the tokens that are inputted into the model and outputted from the model. And the basic concept behind the visual models are three-dimensional tensors of having height of image, width of image, and color depth of the image. And in each combination of these tensors, we have these visual pixels that represent the intensity of the light in that combination. In market model, we are talking about a much more multidimensional structure. Some of the dimensions here represent the time of a transaction, time of a delivery of the transaction, attributes of the product, attributes of the customer class, and so on. And in each such combination, we have these voxels that are not visual voxels, but probabilistic ones representing the probability of certain event to occur, for example, event of a transaction or a cancellation or a competitor repricing. And these market models are only part of the tools that are available for the agentic workflow in order to make the actual decision. That workflow starts with consolidation of data from various sources in order to feed the market model. The market model is then, once trained, it can predict the future market dynamics. These predictions are used then to simulate various scenarios into the future. And one of the scenarios is chosen in order to inject the right decision at every point into the enterprise systems. Let's start with, for example, consolidation of data. Data in that sense would be proprietary data of the enterprise. For example, it's historical transactions, and that data can be enriched from external world by, for example, anything that can be predictive regarding the market, like events, capital markets data, weather, any type of information can be consolidated here in order to feed the market model. Now, the market model is also a deep learning system, as I said before, and that enables us to peek into that brain of market model, just like language systems, and try to understand what's going on, what does it pay attention to, because it includes also attentional layers. For example, here, that's a case where we took one of these market models for one of our customers, and in the data, we knew that there is a new competitor joining the market mid-year. And we tried to understand how much attention does that entrance of a new competitor cause. The new competitor here is represented in yellow. And the market model was quite smart based on the attribute of this new competitor and the attributes of the other competitors to redistribute its attention among the different competitors according to their importance. Now, that's what relates to the peeking into the brain of the market model, but what's maybe more important is the output of the market model. Because as I said, the market model output is multidimensional. It has many dimensions, and we, the engineers in Fetcherr, we like to visualize these dimensions as humans. Now, as humans, we can visualize maybe 2 or 3 dimensions, or maybe 4, as we'll see in a moment. And in order to make that visualization, we need to slice that multidimensional cube at a certain point. For example, fix or attribute as fixed some of the dimensions. For example, set a very specific product, very specific type of customer, specific time of transaction, time of delivery, and play only with a few dimensions, like the own price, meaning the price that we might give our product on the x-axis here, the price that our competitor might choose to price his alternative product, his competing product, on the y-axis. And in that case, we are looking at the expected demand the way the market model sees it. And the market model, the beauty here is that these outputs are automatically generated. The market model knows exactly how to quantify the expected demand based on the historical data. And as you'll can see here, it all makes sense because the blue areas are the areas where the market model thinks the expected demand is going to be quite low. These areas are the areas where our price is higher or significantly higher compared to the competitors. The red areas are areas where it expects high demand. These are the opposite cases, and the market model also sees that equilibrium line between the different types of between us and the competitor. That's where the public, the people that are buying the products don't really care about that difference. And another nice thing here is that if we slice that cube in different locations, we can understand what does the market model think of the difference, for example, between these two markets, where the market model tells us that it thinks the right market is a market where the competition has very low impact compared to the left case, or a market where the equilibrium line moves a little. In that case, it moves to the right by 50 price units, which means that the perceived value of our product in that market is higher compared to the competition. Or here we can see a case where the market model thinks that the right market is much more competitive because its contrast is higher and every cent matters when making the pricing actions. We can also try to see how does this surface of demand change over time. For example, we have pulled this case to see how does this demand surface change over time in correlation to the fuel prices. That's related to airline pricing demand surface. And we can see that when the fuel prices rised up around April this year, the demand was impacted accordingly based on the predictions of the market model. Now, once these predictions are available, they can be used using simulation to evaluate what is the expected reward. So for every pricing policy, we can simulate using a digital twin of the business arena what would be the reward. For example, let's take this case, which is a very simplified case where we treat the business, the decision policy as a two parameters policy based on decision 1 and decision 2. And in every combination of such decisions, we expect a certain reward, for example, a certain revenue. And the nice thing here is that these predictions can be done continuously and reflect the data that flows into the market model. And that flowing in of data into the market model reflects the change in the reward landscape, because reality change all the time, and we as a business want always to be at the peak of the hill. And when the reality changes, these systems know how to move their decision policy according to what happens in reality. So in some cases, you can see, we call these hills, there are several hidden hills under here. Each one of these hills is called, in our sense, a decision-making regime. And in some cases, something changed in the reality, and such a systems know that it needs to move from regime A to regime B, because the hill of regime B is much higher in that reward landscape. Now, the outcomes of these systems can be tested in A/B testing. Whenever we deploy our system, we deploy it on a subset of markets, and that we see as a target group, and we compare the results of that subset to another correlated group, which is the control group. And repeatedly, in every case, we see that these quantitative decision-making systems are showing statistically significant results of revenue uplift, as in here, where the distribution of revenue is shifted to the right significantly in about 7% on average. Now, what I've shown today are a set of tools that are essential tools for bridging the transitioning of the decision-making industry from practices that are based on general harness engineering to practices that are more enterprise-grade, truly reliable agent operations. And in the next workshop, Hadar Sharvit from Fetcherr, who is the VP of Large Market Model and Machine Learning in Fetcherr, will dive into the details of these tools that I presented today. Thank you very much.
All right. So, hello everyone. My name is Hadar, former director of deep learning at Fetcherr, and now entering VP of the market model, which is Fetcherr's proprietary model for decision making using artificial intelligence. In this session, I'm going to go through the process of justifying the statement that is written here down below, essentially why we believe that large language model might struggle with high-stake quantitative decisions, and how by delegating some of the decision to guaranteed tools that have the ability to understand the market and make reliable decisions, we can kind of combine the two tools and kind of see how they benefit from one another. So in this workshop, we're going to talk about the architecting aspects of what we call those quantitative decision agents. And we're going to dive deep, so straighten up and prepare for the following 40-something minutes. Let's talk about how business decisions are being made. So, you know, all of us have been tackled or have been asked a business question in their history or even on a day-to-day basis, right? An airline might ask itself, how should I price a business class seat now, in a week from now, in 6 months, in 12 months from now? Or a sales team might ponder how big of a discount they want to provide for their clients in order to make meaningful revenue indication. And the examples are pretty obvious. They're all around us. And we want to kind of say that in many cases, in order to come up with a meaningful answer, you want to pair up two capabilities. One of them is a predictor, a forecaster that tells us how a market is going to move or how the business objective is going to move into the future based on some signals that we care for. And the other is an optimization process that would reliably consume the predictions of this forecaster to say a meaningful policy of what actions to apply. So an airline might say that based on its forecasting capability, holiday season would be is soon to end, and therefore demand prediction, as far as they understand, that will surely fall, and therefore their decision would be to decrease the prices on that specific seat in that specific market. And obviously there are many examples. Now I'm going to talk about the mathematics behind those two capabilities, starting from the forecasting. What you can see here is a mathematical representation of what we call, or what the industry calls, a point forecast. In the diagram that below the equation that I will outline in words, you can see that the target that we have here is to predict into the future from some point in time denoted by lower script t, whatever signal we are interested in. In the following slides, I'm going to follow the structure of we want to predict demand or the market dynamics as outlined for the most part by demand and other properties. And we're going to use information we know from the past and some information from the future in order to make this forecast accurate. So in this setup, any forecaster, usually a deep neural network parameterized in some learned parameters data, is consumed. The known past information, in this case the known demand, the known in an airline industry or any industry that has products, perishable products that they're intended to sell. What was the demand? What was the distribution of demand in the past? But not only that, there are some features that in the industry might be referred as covariates or exogenous variables. Some of them are known to the past, like for a specific product, what was the representation of the product, what was its associated price. But also there are more information like static information that represents products themselves, IDs, some properties that are invariant in time, and other information that is also known to the future, expected holiday, maybe you know how the weather is going to look like in a high confidence in the near future, or also you kind of know information that is time related, like what day of the week it's going to be, what's going to be information about the time, right? So everything is being consumed by whatever forecaster you'd like. I'm going to follow an example of a deep learning architecture that essentially predict from point T up to what we refer to as the horizon, how is the signal that we care for is going to look like. Now, alternatively, the point forecast is immediately translated to a distribution because some cases businesses want to know something about uncertainty. They want to think about the forecast in means of confidence, and therefore, when you change the neural network output head, you can essentially say, we're not going to predict a forecast. Demand was 7 seats for that specific business class cabin, but rather there is some distribution that could be either parameterized by learning, for example, a multi-dimension neural distribution, or you could describe uncertainty by means of quantiles. We will soon see some examples. Now, this is the first part, and we also talked about an optimization process. An optimization process essentially takes the pre-trained forecaster and says, in this example, the probabilistic forecast, and say, given that we have some reward or some mechanism that the business wants to either maximize or minimize, denoted by U, given some context denoted by S, those are the past information, the price signals, the static information that we have, and a set of feasible actions that could be how to set the price for a specific product, how many inventory to allocate. We want to maximize some objective that is essentially says, let's see how our signal, how demand is going to be looking like in the past, whatever the horizon might be, see what the expectation is, and kind of find an action within the feasible action set that kind of maximizes what we want to achieve, right? This could be, for example, price as an action to maximize revenue, and usually, as you probably, most of you already know, this is never without some hard and soft constraints. So what you can see here, again, we're following the notion of demand and the action of setting the price for specific products. The objective is revenue, so demand times price is usually revenue. So in this case, you can see how we try to maximize the revenue by essentially setting a specific counterfactual price into the horizon, see what would be the associated demand, and this is omitted for simplicity, but the entire context alongside the price that we want to kind of experiment with. We feed it into the optimization, and we let it kind of go. The constraints that you can see here on the side are just few examples that are sometimes relevant when you try to make a meaningful pricing policy decision. For example, when I set a specific price, I never want it to be exceeding specific bounds, or I do not want to introduce high variance in kind of consecutive pricing decisions, or that I want to have some ordering. For example, I would never want an economy ticket to be priced at a lower price compared to, or for a higher price compared to business, right? Business class. Okay, so we kind of defined the fundamentals of how do we think one could use quantitative capabilities in order to answer questions that businesses sometimes have. And I want to kind of connect it to why we think agents work quite amazingly here when they're being provided with those capabilities. And this is mostly for the reason that, you know, the real question that a business might ask is, the questions are open-ended, right? So this is a quote, but it's a general statement of a question that might come up. In this quote, it says, well, we have an investigation where we identify that prices of specific products aren't really keeping up with the demand that we're seeing in the market, and we want to see whether that makes sense. We want to potentially update our pricing policy, right? So we want to kind of have an agent to understand what's going on in the market, understand whether the current policies that we have are sensible, and we're going to see, we're going to let it kind of go. And what I want you guys to kind of grasp in your head before we move on is that we have many reasons to believe that naive or vanilla agents will actually fail in providing a reasonable answers that we can really trust. And they will fail for pretty much the same reason that have resulted from these tools that I outlined to be even needed, right? So naive agents might not have a good enough forecaster that is able to generalize in out-of-distribution scenarios, or they might not even have a forecaster that could do any meaningful forecast at all. I mean, if I were to give Claude Code a query, predict how the price is going to look like, I would argue that it's going to find it a bit difficult. Of course, it doesn't have an optimization process that will allow us to dynamically and consistently use constraints in order to maximize a business objective. And these are examples that we believe that a naive agent might find it difficult to come to success. So this is kind of the motivation I want you all to follow. And in the following slides, we're going to dive into the details of what might be an opinionated way that we think an architecting quantitative decision agent could be made possible. And we're going to see how we see that being rolled out. We're going to dive into some code, so be prepared. We're going to start with the market model, right? The market model is Fetcherr's model for predicting what's going to happen with the market, right? And there are many examples of what are the relevant signals that the market might have. We're going to dive into those in a bit. But what you can see here is a very simple, let's say almost compiled Python code that kind of goes through some of the configurations that one might want to define before running a pre-training multivariate time series forecasting module. So you can see here configurations for array hyperparameter tuning that represents like information about input size, some of the hidden sizes of the internal dynamics of the neural network, learning rate, and so on. Also, we are defining here a set of features. Those are the ones that I've kind of outlined at the beginning. Information about the past that is known, information about the future that is potentially also known. And again, I'm following here an example from a real client that we have in the airline industry. Most of the relevant features here that in this example are outlined as static features represents the cabin, the direction of the flight, and so on and so forth. And we're going to, based on these configuration, run a simple training process. And again, I'm obviously being a bit vague here in the terminology, but one can think of distribution-based loss that will be used as criteria for the deep learning architecture, and some custom deep neural network that is able to consume information from a look-back window and predict that distribution into the horizon. So we're going to let it kind of go through. And by the way, for those of you who are familiar with Andrei Karpathy's auto research, this is fully compatible with that. So you can provide this as context. You can kind of let it run loose. This is hyperparameter on steroids, but we believe that we want consistency for the pre-trained model. We want some guarantees, so we are not yet comfortable kind of moving into that. I'll be able to kind of go into that if you're interested, if you'll jump to our booth later on. And by the way, if those who are interested, this is following the terminology of the open source time series framework from Nixtla. If you're interested in kind of learning more about time series, I highly recommend. We're not working with them. I just feel that they're very, I feel comfortable kind of sharing what they do because they really do best practices, so if you're interested. All right, so we talked about a pre-training. Let's see exactly what are the outputs of the time series framework that we provide. Essentially, what is or what are the dynamics of the market, the way we see them. And this is a simple understanding, simple representation. You know, when we talk about demand, usually we are not talking about a demand value, but rather how demand differentiates, or what's the difference across different price points. And if you've done Econometric 101, you know that demand is usually portrayed by demand curves, right? So what you can see here is a simple process where we load some pre-trained checkpoint of our model. We load all of the information containing feature selection, encoding of the numerical and the categorical features, and so on and so forth. Nothing pretty fancy going on here. And we're going to run through a specific sample that we have been provided with the pre-trained, the forward pass. And we're going to provide, in this example, we talked about general distribution loss. Here we're talking about a quantile forecast that predicts how demand is going to look like, not in the sense of the demand value, but rather the demand quantiles. In this example, we're going through the 10th quantile, the median quantile, which is the 50th, and the 90th quantile. We provide some data class that represents different aggregation that we have on that specific forecast. Looking through the mean of the entire horizon of the demand, looking through the specific revenue. So revenue is price time demand. We kind of talked about this. Explaining some measure of uncertainty that we will soon use. You know, once we talked about quantile, we can assess uncertainty. But not only that, once we have information about the demand, we can look at its higher order derivatives to understand elasticity, to understand where does the maximum of the revenue is being obtained. These are a very simple but still non-trivial understanding of market dynamics. Okay, we talked about the math, we talked about the code of the market dynamic or the market model. Now we're going to jump into the optimization under constraints. So again, for the sake of example, we're running through a very simple data class that go through price constraint, introducing lower, upper demand, introducing some max steps, so consecutive price policy values into the horizon will not exceed a specific threshold. And we have a very trivial but relevant private function that we will then be using in order to apply constraints during the optimization process. In order to find, again, and I want to remind you, we're trying to come up with an optimization that maximizes reward, which is revenue, essentially invoking the forward pass of the market model, understanding how demand is going to look like distribution across the entire horizon. In this example, we're just using SciPy minimized scalar, applying the constraints, and providing a helper function that will help us simulate reward, simulate revenue into the horizon. This is just kind of helper function that will help us have a guarantee of what optimization looks like the way we envision it. And this is an example. I think Uri shared something quite similar previously. What you can see here is that, what you see in here is the revenue landscape as depicted by the market model at a fixed time into the horizon. And the horizontal line that protrudes from the bottom here represents some hard constraint that we have for a specific product represented by, its price represented by Y. In this example, we're essentially saying, if this is the revenue landscape, never have the price policy recommend prices below the point C. And if a global maxima was attained at point A, by introducing the constraint, we are now reluctant to find an optimum policy that is only being obtained with the constraints in a local maxima B. Of course, the revenue landscape is rarely this nice. It is rarely differentiable. But this is just to give you a bit of intuition. All right, we talked about the capabilities. We talked about the mathematical abstraction. We talked about how we can write them in a simple terms in code. We want to plug it into a harness. So what you can see here is how we believe, again, a simple variant of how an agent could use those capabilities, and we're going to go through the process of injecting those capabilities by multiple options, and we'll see how an agent could use them. So one of the first thing that comes to mind is that each one of their capabilities, we talked about the market dynamics prediction, we talked about the optimization process. Let's kind of wrap them in tools. This is just one of the example, and again, we're not working with Claude, but what you can see here is that we're using Claude Agent SDK, which is pretty much Claude code-like in the sense of the functionality that you might expect to be. So if you're working with Claude code, this should be pretty straightforward for you to kind of follow on. We're providing a pretty simple wrapper to the prediction of the market dynamics. So I hope you guys can read, but I'm going to be a bit verbal going through that. What you can see here is that the Predict Market Dynamics tool is essentially a tool that is provided with configuration in a Pydantic-like structure. So the input would be verified by the agent before invoking the actual prediction of the market dynamics, which is abstracted in a capabilities.py file. This is the capabilities we talked about before. And we're returning a structured output with a context, exposing some of the market dynamics output that we talked about, the quantiles themselves, understanding of elasticity, and so on. And we kind of go through the process of taking each and every one of our capabilities and wrapping them with a designated tool. What you can see below, and of course for brevity I haven't included all of the tools, what you can see below is how Claude SDK provides an abstraction to an MCP server. So there are the data capabilities tools, which are essentially, these are the buckets in GCP. Please go ahead and fetch the relevant data in order to, and again, I want to remind you, we're going to provide an agent with a question of, are prices here sensible, right? So we want to provide it with real data. We have an MCP tool to help the agent kind of fetch the relevant data. We also have what we call the Fetcherr capabilities MCP that is essentially a thin wrapper, a server, if you will, of all of the tools that we talked about. Soon you're going to see how I'm using specific clustering of the tools. At the bottom here, we have data tools that kind of allows the model, allows the agent to fetch real historical information about the market. We have the large market model tools, which is essentially the prediction of the market dynamics, the optimization, and some tools concerning evaluation. So, okay, once we have the tools, we want to define some structure that will allow specific tools to be invoked by specific subagents. In this example, you can see, and again, Claude SDK abstract those pretty nicely if you're interested in kind of diving into that. We have two functions that essentially, one of them is an analyst factory, and one of them is an initializer of an analyst. We're going through the process of defining three designated subagents and one kind of orchestrating agent. The orchestrator is going to be a revenue manager. It's going to have a system prompt that is relevant to what might you think would be relevant for a revenue manager that has under its disposal three subagents. Each one has the designated capabilities, understanding the dynamics of the market, understanding how to provide pricing policy, and a QA analyst that will kind of help making sure that the predictions and the policies are sensible. And this is how it's being defined. Again, this is fully runnable code. All right, the final thing, and this is more kind of for meta-analysis. Since we're using specific capabilities, we want to make sure that we hook them and kind of log whatever information we care for in a way that is customizable. So usually when you kind of fire a tool, there's a post-tool use that is being invoked, and Claude SDK has a specific hook matcher that kind of allows you to grab specific functionalities. For in this example, after a tool has been called, you want to kind of catch that. You want to do some custom behavior. In this custom behavior, we want to define what we call grounding. We want to see when the agent was going through its reasoning, whether it was utilizing the specific tools that we have defined. So this is just something that I wanted to add for completeness. At the end of the day, Claude agent options consumes all of the things that I outlined right now. So there's the general revenue manager prompt, which is the system prompt that we have for the agent that orchestrates. We have all of the allow tools, the MCP server, the subagents, and the hooks that I defined. And we're kind of going ahead and letting this agent run. And this is a simple query loop that we provide just for kind of logging and printing the results as they go. but this is pretty much it. All right, so we talked about the capabilities, the capabilities in terms of real Python code. We talked how you might connect them to a harness. And we want to run through an experiment. And the following experiments, 2 agents will be asked the same question. One of them is a Claude agent, essentially a Claude Code harness. It has reasoning, it has web access, it could write and run its own code, it could do whatever the hell it wants. On the other hand, there's the Fetcherr or the market model or the agent that has the capabilities that allows it to understand the market. But other than that, it's going to be pretty much the same. We're going to ask them a simple question: is the price right? Now, what you see here is real, obviously anonymized data from one of our clients. You can see here in a year-over-year analysis how demand has been reduced for a specific product at a specific market by 22%, whereas prices for that specific product have increased by more than 60%. And we kind of want to kind of provide this context to the agents and say, guys, is this sensible? The answer is not trivial. One might say it is because the price increased that we are seeing demand decrease, but this might not be the answer. Demand could be decreased because something happened, something else, right? This is the data, the outputs. You know, we talked about the fact that we are hooking on whatever tools that were called. The output here that you can see here at the top here is kind of the directory structure of the, let's say, the vanilla agent, and on the bottom, the agent that has the capabilities. They both went ahead and provided some markdowns with some of the thought process that they've done, but ultimately the 2 provided a recommendation CSV, increase the price, decrease the price by how much, and we'll see how they differentiate. Before I get into that, and maybe you will start thinking about the intuition, if you were to guess what were the recommendations of those 2 agents, would they even be the same? I want to go through some of the kind of meta-analysis when it kind of seeing what the agents did. So they were bashing away, right? So Claude agent, it wrote some Python script, it ran some statistic, it used pandas, his favorite tool, and it kind of produced CSVs that help him understand the historical data, the patterns, the correlation for that specific product and that specific market, and it kind of did quite a lot. The market model agent, on the other hand, well, it has the capabilities. So he used them extensively, and not only that, he aggregated the results of utilizing the tools that hide behind the scene the capabilities, parsing them, building product lists on top of them, aggregating optimization results, and take it at face value, was using much more tools. Now, if you cluster the tool call per analyst, so we talked about the fact that we have 4 agents, right? 3 of them are analysts, and the one that orchestrates the 3 is a revenue manager tool. One thing that we found quite interesting is that the Fetcherr, the tool that the agent that has the capabilities, was going through the process of invoking, predicting how demand is going to look like. But for one of the products, it has identified that there is some uncertainty in the prediction. It could be due to the fact that historical data was not substantial enough, but regardless, and this was the work of the QA analyst, he flagged using the evaluate forecast tool that there is high uncertainty in the predictions of one of the in one of the products in one of the market. He kind of raised it to his boss, the revenue manager, who in turn redispatched the price analyst on the subset of the market, and therefore you can see kind of the spike. So they were kind of playing between one another, flagging some concerns, going back to the capabilities and going through the process. At the end, in a market where there are 6 specific products, the Fetcherr analysts have recommended to ship 5 prices, so 5 price recommendations, and one of the markets where he identified uncertainty, it had flagged it for the revenue manager, and this was part of the rationale markdown and part of the recommendations. The unaided agent, of course, shipped everything. It had no mechanism to evaluate uncertainty in the market. All right, so kind of zooming into one of the products, at the top you can see just catting the recommendation CSV in a product. And again, the top is the unaided agent, and at the bottom, the Fetcherr agent with the capabilities. For a specific product that at that specific point in time was priced at $1,100, the vanilla agent was recommending a price increase by $200, and the Fetcherr agent was actually recommending a price decrease by about $250. So they were essentially having the same data, different reasoning, and absolutely different conclusion, both in magnitude and in direction. Let's see some of the thought process. What you can see here is an estimation of revenue and demand, and at the kind of white dot, the current $1,100 of that specific product of interest, right? Let's see what the Fetcherr agent understood. So the Fetcherr agent kind of went ahead and invoked the market model and understood that due to the fact that at this specific price, there's an elasticity that in absolute value is greater than 1, he recommends to decrease the price. And he found that in an unconstrained setup, the decrease should fall to the 828 part where elasticity gets his maximum. Elasticity, by the way, is how much in percentage does price change cause to demand change. And kind of quoting from the rationale at the right here, this is just a quote from one of the output assets of the agent. Demand on the route is elastic. Every 1% price reduction yields about 1.4% more bookings, more than offsetting the fare reduction in revenue terms, right? So it did its analysis based on grounded tools that provided it understanding of how the market is going to evolve, and therefore how to recommend an updated price. Ultimately, the revenue manager agent has used this and kind of invoked the price optimization tool. It has found that because it is constrained, and by looking through the entire set of departure dates, it could not meet the price where maximum is really obtained, but essentially decided to sit not far away from there at $863. In the process and in the rationale, it has identified that there is a holiday happening at that departure, and kind of use that in order to kind of showcase that averaging demand across price in this market at specific dates where in some cases demand might be even higher due to holiday could result in kind of pricing much higher, and ultimately it had fixated at similarly to the market model at $863. The revenue manager, quite satisfied, took those recommendations, rounded up for simplicity's sake, and shipped the fare, the price, $850. And this is what it done, right? In estimation of the revenue, this has caused more than 6% uplift in that specific product. Now, the unaided agent, it was trying its best. It really did. But in the process, it has confused correlation for causation. It had ran analysis on correlation in specific markets that do not necessarily correlate with one another. And I'm going to quote you once again. Demand elasticity is negligible in a specific bucket of dates that it was investigating, correlation of nearly zero. So raising the floor carries near zero demand destruction risk. Essentially, it has wrongly identified that there is no correlation. What it had done by mistake is correlating products that shouldn't be correlating with one another. It was never fixating a specific product and varying the price in a counterfactual manner, and therefore have decided that it could increase the prices without the demand to fall. But ultimately, and unfortunately for him, elasticity is a real thing, and in the process, in a kind of unbiased revenue estimation, it has resulted in almost 8% revenue uplift, or a negative revenue uplift. All right, so what we have seen here, let's talk about this whole pipeline end-to-end and kind of call it a day. We talked about a general harness. We defined one manager that runs a loop, reviews it, and kind of aggregates whatever it had found. We talked about sub-agents that has specialties, They split the work, each get its own tools. They don't share context. They don't confuse with tools that might be similar. They have a QA mechanism that is unbiased and is able to check the assets of its counterpart subagents. And crucially, they all use quantitative capabilities. This is where the mathematics is at. This is where the formulas are being implemented. This is where the revenue manager agent knows that he is not expert in, and he is delegating in order to make a meaningful and reliable answer. And of course, by grounding and seeing what's happened in the process, he is able to come up with recommendations that, compared to an unaided agent, are substantially different. So if there's one thing I want you guys to take from here, is that we feel that there is great power by joining large language model capabilities of orchestration and agentic harness development, but knowing when and how to delegate the capabilities that will tell you that you can trust and rely the outcomes. So while the large language model orchestrate the capabilities, like the one that cover all of the intelligence that we develop in Fetcherr, those are the one that carries the guarantees. So thank you so much.